Today what we're going to be looking at is, well, you remember last week we talked about parametric curves. So another way of thinking about curves in the plane, rather than simply writing down one coordinate in the Cartesian plane as a function of the other, like y equals f of x, and rather than just writing down an equation like x squared plus y squared equals 1 or something like that, what we do with the parametric systems is we make both x and y be functions of some additional coordinate t, or it doesn't have to be t, but often we use t for the parameter, and then we watch what happens to the point x of t comma y of t as t changes. So we talked about all of that. We talked about how you can graph things using parametric curves, and hopefully you were able to take a chance last week and play around with some of those tools that I gave you online, where you can actually plug in some various functions and watch the plot happen. And then also, of course, we talked about how you do calculus with the parametric curves. So a lot of what you do when you're doing the calculus stuff is it's not really that different, right? Like you're just going back to doing basic calculus stuff, except that now you've got these two different functions to worry about instead of one. And one thing I did want to mention really quickly here, and let me bring it up, just because I did not mention this last time. So when you're doing parametric curves, you have to be careful when you're doing second derivatives, okay? Because you would maybe think that the second derivative of y with respect to x would be equal to the second derivative of y with respect to t divided by the second derivative of x with respect to t, but this is not true. So you have to be a little bit more clever about this sort of thing. And what you end up having to do is you have to take the derivative with respect to x of dy by dx. Now, what you know is that the derivative of y with respect to x, this is dy dt, and give me a second to write this down, over dx dt. So this is true, and we worked out why this is last time. But now, we just have some new function in terms of t's that we are now differentiating with respect to x. So we have to repeat the same argument as you did last week. And it's not like it's an especially complicated thing, but it does give you a little bit of a messy formula here, because you end up essentially with something that uses the quotient rule. So this comes out to be, and let me write this down carefully to make sure that I'm not lying to you here. This is going to be, actually, let's write it out with primes because it's a little neater. So it's x prime y double prime minus x double prime y prime divided by x prime cubed. And this is just what you end up with when you apply the same reasoning as we did to take derivatives with respect to x, but you're now applying it to this function. So I will leave it as a little bit of an exercise for you to actually prove that this formula is correct. If you're interested, you can just memorize this formula as well. In fact, you may want to memorize this formula, but I think it is instructive to just go through the same procedures as we did last week and derive this. So there we go. We've got our formula written down here. And give me 1 second here. Yeah, so if you want to see some other examples of this kind of thing, if you go to wolframalpha.com, they have a bunch of widgets that they call them widgets. They're little tools that you can use, and one of them is about second parametric derivatives. So you can use that kind of thing as well. But in general, it's not like it's that complicated. I mean, it's a long formula, but it's not like there's anything particularly hard going on in it. We're just taking some derivatives with respect to t. And notice that when I wrote it in prime notation like this, I mean x prime is dx by dt and y prime is dy by dt, of course. Those are the derivatives with respect to t. Okay, so now that we have covered this one quick thing about parametric curves, I want to move on to talking about something else this week, and that is the polar coordinate system. So let's think about points in the plane and how we can describe them. In one sense, the way that we are most familiar with is also one of the ways that is kind of the most obvious, right? So at least to us, it's now pretty obvious how to think about them this way. We think about points in the plane by saying, okay, we're going to put perpendicular axes, x and y, and then we're going to take some point and we look at, like, we project it onto the x-axis and onto the y-axis. So we look at these lines that are parallel to x, parallel to y, and we look at where these lines meet the axes. And if this is the point A on the x-axis and this is the point B on the y-axis, we describe this point as A, comma, B. And this is really the foundation of algebraic geometry. It gives us a beautiful correspondence between algebraic equations and geometric shapes, right? For instance, this is how we see that the algebraic equation x squared plus y squared equals 1, the points whose coordinates satisfy this. I'm sorry, once again, we're having some issues with focus on the camera. The points that satisfy this equation are just the unit circle. So we have this really nice correspondence. And of course, this ideas similar to this kind of go back a long way, because you can sort of think of this as two different number lines that are placed perpendicular to each other. And so in some sense, the number line is really the most basic form of this, where we take a straight line and we mark it up with numbers. But this is called the Cartesian coordinates after the mathematician Descartes. This is also sometimes called rectangular coordinates. And it's probably not too difficult to think about why. Because we're dealing with these two perpendicular axes, everything that I'm going to be talking about is going to involve looking at a rectangle of some kind, right? I take some point here, and I'm looking at a rectangle formed by the x-axis, the y-axis, and then this point. Okay, so that's where the name rectangular coordinates comes from. Sorry about that. Okay, so these are the rectangular coordinates here, or Cartesian coordinates. But these are not the only way that we can describe points in the plane. There are other ways of sort of algebraically talking about them, or geometrically measuring to locate the points. And one of the other ways of doing it that is most useful is called polar coordinates. So I want to talk about how this polar coordinate system works in this lecture, and then next time we'll talk a little bit about how you do calculus with it. So here's the idea behind polar coordinates. We're going to leave up the x and the y axes for the moment, just so that we can refer back to them as we need to. But here is how I would like to specify a point. We're going to specify the point by using two different numbers. Now, that is not surprising. We've got a plane, it's going to take two numbers to give a point. And the way that we're going to specify this is we're going to specify a radial coordinate, which is going to be called r, and then we're going to have an angular coordinate. Apparently I can't hold my pen. Angular coordinate, which is usually written with the Greek letter theta. So this thing that looks like an O with a horizontal dash through it is actually the Greek lowercase theta. Actually, the uppercase theta looks pretty similar, but this is a lowercase theta, just in case you're curious. Now, here's the idea behind this. We're going to write these as pairs r comma theta. And here's the rule for how you go from an r comma theta pair to finding a point. Okay, so we actually start with the angle. The angle is in radians in the counterclockwise direction, starting at the x-axis. So theta is going to measure how far I go around like this. So I start here and I rotate by an angle of theta. And then what I do is I start at the origin and I move out in this direction a distance of r. And this is my point, r comma theta. So the angle coordinate tells me the angle that I make with the x-axis, and the radial coordinate tells me how far in that direction I go. It's actually not really that complicated of an idea once you think about it, right? If I want to tell you how to get to a point, one way I can do is I can say, okay, stand at the origin facing along the x-axis. Then turn so that you're facing along this angle, and then walk a distance of r. So it's actually a pretty natural way of talking about things in some ways. But there are a couple of complications that we don't get when we're talking about Cartesian coordinates or rectangular coordinates. And one of the things that we lose when we go to polar coordinates is with the Cartesian coordinates, every point can be uniquely expressed by one pair of numbers. If I give you a single point, you can only express that in Cartesian coordinates one way. Well, technically, I guess what you could say is, but it depends upon where we place the two Cartesian axes, right? We could move the axes around in the plane. Yes, but once you pick your coordinate axes, every point gets a unique pair of numbers associated with it in Cartesian coordinates. And that is no longer true here. The reason that that is no longer true is, well, there's two reasons actually, and I want to explain both of them. The first problem is, notice that r comma theta is the same point as r comma theta plus 2 pi k, where k is any integer. In other words, if I take my angle and I change it by a multiple of 2 pi, oh, give me 1 second, I need to help somebody out. Sorry about all the disruptions today. We have a new adjunct coming in, and I was helping her get situated and things, and so hopefully we will be done with disruptions for this video, but I make no promises. Okay, so one of the problems then is that if I want to use these polar coordinates, then the angle isn't unique. I could specify another angle and it would get me the same point. But here's the other problem. What if r is negative? Well, in order to define what it means when r is negative, we say that if r is negative, you go in the opposite direction. So you go the same distance, but the opposite direction. So this point down here would be the point minus r comma theta. However, that is the same as r comma theta plus pi. So there's these many different ways of expressing each point in polar coordinates, except for the origin. Well, sort of except for the origin, because the origin itself is also weird. The origin is literally anything with a radial distance of 0, but the angle doesn't matter at the origin because we're not actually moving. So we can spin around as much as we want, and we're still just at the origin. There's no actual change here. And thus, we get this sort of weird situation where points are not uniquely defined using polar coordinates. And because of this, we tend to, well, that's sort of a downside compared to the rectangular coordinates, because having each point uniquely associated with a single pair is pretty nice. Fortunately, it turns out that losing this property when you go to polar coordinates isn't necessarily always the end of the world. It's not necessarily that big a deal. It's just something you have to keep in mind. But otherwise, you can talk about like whatever you would like to talk about, and it works just fine. and, everything just kind of goes the way it goes, okay? So, yeah, I mean, we can sort of do whatever we want that way. Now, one thing this does mean, of course, is that if you're locating a point and you want to give the polar coordinates of that point, you have a bunch of choices to make in how to do that. So depending upon how you've been asked to give the point, you may want to make different choices. For instance, one common choice that people make is to always choose an angle between 0 and 2 pi, and then always choose a positive radial value. Because if we insist that the angle is between 0 and 2 pi, and we insist that the r coordinate be bigger than or equal to 0, well then all of the points can be uniquely written subject to those conditions, except for the origin, which is still an exception, but we don't really worry too much about the origin because it's just the one point, and it's the origin, it's special anyway. So that's one sort of convention that you can use. If I give you a point, you can write down radial and angular coordinates for it uniquely subject to those conditions. But there's other conditions that I could choose instead and that I may want to choose in some situations. So let's take a minute to think about locating some points here using polar coordinates. And briefly, I should tell you, before I choke myself to death, why are they called polar coordinates? Well, the reason they're called polar is because think about what would happen if you were standing at the North or the South Pole. Think about the latitude and longitude lines. The one of them are going to be spinning around you at various angles, and the other one, so the longitudinal lines, will be spinning around you in various angles, and the latitude lines are going to be determining the distance that you move away from the pole. So polar coordinates, because this radial and angular idea looks kind of like the latitude and longitude system at one of the poles. Now, why would you ever want to do this really quickly before we get into how you locate points? Well, the reason you'd want to do this is because there are a lot of physical systems that tend to exhibit what is called rotational symmetry. In other words, you might have a system that is really, really nice under rotations. It doesn't change when we rotate around the origin. Or maybe it changes, but it doesn't change a lot. And things like that can actually be expressed using polar coordinates and equations in polar coordinates in a really nice way. For example, we're going to talk about more graphing of equations and things in a minute, but just consider the equation r equals 1. Well, this is satisfied for any given angle, and the only condition then is that the radial coordinate should be equal to 1. So if this is my x coordinate, this is my y coordinate, what I end up with is just a circle of points, all of them a distance of 1 from the origin, which means that what I've got is the unit circle. More generally, if I set the radial coordinate equal to capital R, where capital R is some fixed number, I am going to get a circle of radius r. So we can see that one of the nice things about this system is that circles are now defined using linear equations, whereas in the Cartesian coordinates, circles are defined using somewhat complicated, they're not terrible, but they're a little more complicated, right? Now, the problem, of course, is that this is no longer true if we're talking about a circle that is not centered at the origin. If the circle is not centered at the origin, then everything becomes a mess again. So this is why polar coordinates are kind of I don't want to say specialized necessarily, but they do have a place where they're convenient to use, and it is sort of a restricted set of circumstances where polar coordinates are really better to use than other types of coordinates. However, they do come up a lot because, like I said, there are a lot of systems that end up being rotationally symmetric about some point. And then in physics, for example, we can write down equations that are really, really nice, much nicer to work with than if we wrote them down with Cartesian coordinates. Okay, so let's take a look at identifying a few different points. And I'd like you to, at each one of these, maybe watch me do the first couple, but then, as I write down different points, take a minute to see if you can locate the point first. So, let me just make a new set of axes here. And when we write polar coordinates, we do often put the Cartesian coordinates in there just to help us out a bit too. So let's suppose that I want to locate the point 1 comma pi over 4. Well, the point 1 comma pi over 4 means I go up to an angle of pi over 4, and then I go out to a distance of 1. So I would be a distance of 1 away from the origin, and my angle would be pi over 4. What if I had something like 2 comma 3 pi over 4? Well, 2 comma 3 pi over 4, first of all, 3 pi over 4 gets me halfway through quadrant 2. So this is my 3 pi over 4 angle. And then I have to go out a distance of 2. So there we go. I am up here at a distance of 2, and my angle is 3 pi over 4. Now, what if I did something like 1/2 comma 7 pi over 6? Are you able to take a moment and see if you can locate that point on the plane? All right, so hopefully you will pause this, take a moment, actually do this. Now, the angle 7 pi over 6 is going to take me around to pi over 6 past the left-hand side of the x-axis. Sorry, I'm trying to think of how to express what I'm doing. But we go around by pi, and then we go an additional pi over 6. So this is the direction that I'm going. And then the distance that I want to go is just a distance of 1/2. So that's not really out very far, and it's approximately right here. What if we had something like the point 3/2 comma, what do I want to do here? Let's suppose that for my angle, I want to do 5 pi over 3. So take a moment and see if you can find that. Okay, so 5 pi over 3, that is actually the same as going back from here by pi over 3. So we end up along this direction, right? So there's my angle of 5 pi over 3. And then my distance radially is supposed to be 3/2. So actually that's not quite, that's approximately far enough. I think it looks similar to this point, but we're at a different angle, so that's okay. So there we go. We've been able to locate these points in the plane. Now, the thing that can get complicated here, right, is that there's other things that could happen that maybe make things a bit more tricky. For instance, okay, I should just redraw this rather than trying to erase so carefully. So, for instance, what if I were to look at a point where instead of 1 comma pi over 4, we had -1 comma pi over 4? Well, in this case, my angle is still pi over 4, just like it was last time, but this time I have to go in the opposite direction, a distance of 1. So I'm actually going to end up down here in quadrant 3 for this particular point. Again, simply because the radius is negative here. And you'll notice that, of course, this is the same as doing 1 comma 5 pi over 4, right? Because 5 pi over 4 would take me around to this angle, and then I would do this distance. And I apologize. I do not know why my camera's having so many issues. I wonder if that makes it any better. Sort of, I guess. I don't know. Anyway, so there we go. We can locate these different points, but there are some tricky things that can come up. Similarly, if I have something like, what if I had 2 comma 13 pi over 6? Well, this is the same as 2 comma pi over 6. Because if I subtract 2 pi from the angle, I end up with pi over 6. I can also think of this as I go around a full 2 pi, and then I go around an additional pi over 6 here. And then I go out a distance of 2. And there's my point. So you can see that, yeah, there's some situations in which this is a little bit trickier in some ways than the rectangular coordinates, but it really isn't too bad. Now, one of the things that we want to talk about is how do you translate back and forth between the r theta coordinates and the x and the y coordinates? Well, it turns out that this is not too difficult to do. In fact, you might find it enjoyable to see if you can work this out for yourself. So maybe take a minute to try to think about this. In particular, I'm going to draw a picture here and encourage you to take a minute to think about this. Okay, now I'm getting a phone call. Possibly. I don't know what was going on there, but okay, sorry. I thought it might be an important call, so that's the only reason I stopped. So I'm going to draw just an arbitrary point here and say, okay, let's suppose that I have an angle theta and a distance r. So this is the point r comma theta. Now, what would be the x and the y coordinates of this point? Can you figure it out from this picture? And I'll give you a hint, it involves trigonometry, which maybe kind of is obvious since we've got these sort of natural triangles going on. Okay, so were you able to come up with anything? The idea here is this is a right triangle. The x coordinate is just going to be whatever I get along the base of this triangle. Holy crap, this thing is still having issues with getting really bright. I will try to stand in a place that keeps it from getting overly bright, but I don't know what's going on with that. And so, well, this right here is going to be r cosine theta. And the point along the y-axis, well, that's going to be this side of the triangle here. That is going to be r sine theta. So like I said, it's not actually a very complicated thing. It's just coming straight out of trigonometry. And so we have this nice correspondence here where we say x is equal to r cos theta, y is equal to r sine theta. So if you've got something written in terms of your polar coordinates, you can rewrite it in terms of x and y coordinates by just using these formulas. Now, the other direction is a bit trickier. And the reason that the other direction is a bit trickier is because, well, we have to worry about the fact that there's multiple ways of writing something down. So the way that we do the other direction is we notice that if this is the point x comma y, then what we have is that r squared is equal to x squared plus y squared. So that's the first thing that we have. And the second relationship that we have for finding this is we know that the tangent of theta is going to have to equal y divided by x. Now, you would like to be able to say that theta is equal to tangent inverse of y over x, but this is only partly true, or it's only true sometimes. The reason that it's only true sometimes is because remember that the range of arctangent, or tangent inverse, is actually just minus pi over 2 to positive pi over 2. So you actually have to be really careful because maybe you're dealing with an angle over here instead. So you have to, when you convert from Cartesian into polar coordinates, you can find the radius in this way, and this just follows from the Pythagorean theorem. You can find the tangent of theta in this way, that's no problem. But then to actually get the angle, you have to say, okay, we need an angle with that tangent, but we need to be careful about which particular quadrant we are in. So that is where things get tricky. For instance, if I wanted to talk about, what's a good point to do? Let's say that I want to do this point here. So I want to do the point with coordinates, and I don't want this to be super complicated. So let's say that it has the coordinates 1/2, comma, square root 3 over 2. Well, then what I can say is that the radius here is going to obey r squared equals 1/2 squared plus radical 3 over 2 squared. Now, when I write that down, what we're going to have is r squared equals 1. This means r is plus or minus 1. And then what we can do is we can say, okay, the other thing is that the tangent of theta is going to be equal to radical 3 over 2 divided by 1/2, which is radical 3. The last thing I want to do is I want to say, but this thing is going to be in the first quadrant. And in the first quadrant, the angle should be between 0 and pi over 2. And I want to pick my radius to be positive. So we can describe this point as 1, comma, pi over 3. It satisfies both of these conditions. Okay, sorry, we are having the world's worst luck today with actually getting through a recording. Like, this may be the most interruptions in a recording in history. We should probably contact the Guinness Book of World Records. Moving back to where we were at. So we located this point using polar coordinates now. Now, the nice thing is that going the other direction is actually very, very simple. So if I give you some sort of a point, like let's say that I give you the point let's say 2, comma, this would be about 5 pi over 6. Then in radial coordinates here, well, this is really straightforward because now we just say x is equal to 2 times the cosine of 5 pi over 6, and y is equal to 2 times the sine of 5 pi over 6. And then we wonder why none of the pens in this entire campus work correctly. Okay, that's just sad. Okay, I think this is going to work, so we're going to go with this one now. And at this point, it's a pretty straightforward thing to just calculate what each of these things are. We know that the cosine of 5 pi over 6 is minus radical 3 over 2. So this is 2 times minus radical 3 divided by 2, which is minus radical 3. And then this is going to be equal to 2 times 1/2, which is equal to 1. So the rectangular coordinates are going to be minus radical 3, comma, 1. And there we go. So converting back and forth between these points, fairly nice and simple. Now, what about graphing things? Well, there's a lot of different things that we can graph using polar coordinates that come out really, really nicely. And a good example of this would be, it's not just circles. Like I said before, it's easy to graph circles, but there's other things that are fairly straightforward to graph as well. And these are spiral shapes. So if I have something like r is equal to m theta plus b, and for the sake of simplicity, let's restrict ourselves to theta bigger than or equal to 0 for the moment. What is this thing going to be? Well, it's going to be a spiral that starts at a radius of b, and then the radius is going to change by a rate of m as theta goes around. And so what are we going to end up having? Well, we're going to end up with something like this. We're going to start out here at b, and then we're going to spiral around, and by the time we get back here, this distance here is going to be 2 pi times m. And then we're going to keep on spiraling around. Okay, my ability to draw spirals is limited, but, right, so I come back around. Once again, I have moved over by 2 pi times m. And so we get this nice, pretty spiral shape going on here. Now, what would happen if we allowed theta to start becoming negative as well? Well, then we would end up spiraling inwards. Eventually, we would hit the origin, and then our radius would start being negative. And so we would get a spiral, but it would start spiraling in the opposite direction. And this is where my graphic skills become limited to the point of nigh uselessness. Okay, so what I am going to do for you, though, is I'm going to give you a link to a polar coordinate plotter. And what I'd like for you to do is to try plugging in some different equations like this and see what you get for these different spirals, and see if you can kind of figure out how to get those spirals. Because, like, let's say that we have just something where theta is allowed to go negative and b is equal to 0. So what if I had something like r equals 1 over 2 pi times theta, and we're letting theta be less than or equal to 0. Well, when theta is equal to 0, this one would be at the origin. And then as theta grows, theta is going in this direction, but my radius is going negative, so we actually go in this direction. Until eventually we get over here. And this distance, well, this is going to be over at x equals -1. Okay, so we keep on, and then we keep on spiraling around in this manner. The next time we'll come through -2, and so on. Okay, so I have not done the world's best job of making this spiral. This is why I think messing around with one of the computer systems might be more beneficial for you. But hopefully you can vaguely get the idea of what's going on here. So spirals in polar coordinates are actually just linear equations. Now, in nature, we get spirals all over the place, right? For instance, we see spirals happening in a lot of seashells. Various creatures, they produce their shells in spirals. So spirals show up there. We can get spirals in galaxies. We can get them in weather systems. So all of these are situations where it might be useful to use polar coordinates because the equation for the spiral becomes really, really simple. Now, you'll notice that the equation, if you tried to write an equation for this curve, or for the one I erased a minute ago, using Cartesian coordinates, it would be a royal pain to do that. Another thing that I want to observe here, and this is another sort of thing that I want you to play with on the computer-generated graphics, but I'm going to just show you like one quick sketch here, is what if you have something like the radius is equal to the sine of theta? Well, then what's going to happen is the radius would start at 0. As the angle increases, we would come out to 1. But then, as the angle goes up to pi over 2, we would come back to 0. And then, as it goes from pi over... Sorry, not pi over 2. As it goes up to pi over 2, we come out to a distance of 1. As it goes up to pi, we come back down to 0. Then as it goes from pi to 3 pi over 2, it becomes negative. And so it actually traces out this same curve again. And then as it goes from 3 pi over 2 to 2 pi, again, the radius is negative, so it traces out this same curve. And so what we get is this almost flower petal shape, but it's only in the one spot. And you can play around with other types of things like this. Like, let's say that we do r is equal to the cosine of 3 theta. Well, what you're going to end up doing here is you're going to end up going from 1 to 0. So you start out here at 1. You would come back to 0 when 3 theta is equal to pi over 2. And then you would start being negative from 3 theta being pi over 2 to pi. And so that's going to get you a thing going out in this direction. And then it's going to start coming in again. And what you find when you do this is you end up with this like triple petal type thing going on. So I'm not going to finish doing this graph. I think seeing it done by the computer might be a little more useful than watching my terrible attempts at trying to draw, just because I am incompetent at drawing. But you keep on going like this, and you end up with this really pretty flower petal kind of structure. So I want you to go ahead and play around with these, see what you can see in terms of the patterns that you get, the number of petals that you get, and all of that kind of thing. And next time we'll kind of finish talking about these after you've had a chance to play with them for a bit. And then we'll also talk about how do you do calculus with polar coordinates or in polar coordinates. So for now, though, I'm going to stop this here, and hopefully next time we won't have 18 different interruptions as well.